Welcome to Efiwe, excellence without stress.
Welcome, guys, to Efiwe, excellence without stress. And I remain your favorite chemistry tutor, Godson. Now, certain processes in chemistry you would notice would actually lead to the production of electrons. And when those electrons begin to flow, you will find out that current is generated and we have electricity. Let's get to understand exactly how this happens by understanding the process of the redox reaction. Now, the redox reaction is basically an acronym for two words, reduction and oxidation. And that acronym for these two words are two different reactions that are opposite in action, however, they occur simultaneously. In this study, we are going to be looking at the different definitions of the redox process. We'll talk about oxidation number, properties of oxidizing and reducing agents, then get into balancing a redox equation. So let's get into it. What are the different definitions of oxidation and reduction? As I said, redox, two reactions, oxidation and reduction, however, they are opposite, which means if oxidation is something, reduction has to be the opposite. If I say oxidation is fat, reduction is slim. If oxidation is tall, reduction has to be short. And basically that. Okay, with that said, let's get into the definitions. So the implication is that, as you notice, if we say that oxidation is the addition of oxygen, reduction is the removal of oxygen. When we say that oxidation is the removal of hydrogen, reduction is the addition of hydrogen. When we say that oxidation is the addition of electronegative substances, reduction is the removal of electronegative substances. And when we say that oxidation is the removal of electropositive substances, reduction is the addition of electropositive substances. Now, the first four definitions I gave or descriptions are obsolete definitions. They do not apply currently because they are not all encompassing. Hence, the most acceptable definitions of oxidation and reduction are those with respect to loss of electrons and increase in oxidation number. So let's take that now. The most acceptable definition of oxidation is that oxidation is the loss of electrons, while when you are considering reduction, it will be the gain of electrons. On the other hand, if you are dealing with oxidation, it is the increase in oxidation number, while reduction is the decrease in oxidation number. I actually have an acronym to help you remember these two major definitions, and that acronym is Oyile Rige O-ion Redon. Oyile Rige O-ion Redon. So it's more like oil rig O-ion Redon. So let's look at that. I'll put it down and show you guys what I mean. Going to our board. The implication is that if I want to describe the redox process, I can simply write the redox process. So if I want to describe the redox process, I can simply express it as Oyile. What does Oyile imply? It simply means oxidation is loss of electrons. Rige, taking that out. So Rige is the opposite, which means reduction is gain of electrons. So I said my acronym is Oyile Rige O-ion Redon. So the other way of describing it is O-ion Redon. So what does that mean? Oxidation is increase in oxidation number. It makes sense to say oxidation is increase in oxidation number. Yeah, it makes sense. While reduction is decrease in oxidation number. So it's like the opposite. So anything you have for oxidation, the opposite would be reduction. Now, as I said, my acronym is Oyile Rige O-ion Redon, or you could just say oil rig or ion radon. Whichever one is easy for you to remember, just keep using that over and over and over, and as you use that, you will notice something, and you will get to have this in your head. Now, having said that, let's get back to our description of the redox. So as I was saying, anytime we're talking about redox, the most acceptable definition is with respect to electron transfer and oxidation number, and they both describe loss of electron for oxidation and gain of electron for reduction. However, it means increase in oxidation number for oxidation and decrease in oxidation number for reduction. Moving ahead, let's talk about oxidation number. Oxidation number is a numerical value that describes the electrical activity of a substance. It is in most cases equivalent to the electrical charge of a substance, or the electrical charge a substance possesses. We are now going to look into the simple rules to determine oxidation number. Rule number 1. The oxidation number of a neutral substance is equals 0. What does this simply mean? Once you are dealing with a neutral substance is a substance that does not have a charge. That particular substance will have an oxidation number of 0. Let's look at the screen. So if you take this out, you will notice that if I want to express the oxidation number of something like sodium, if you look at sodium, okay, before that, every symbol has 4 pieces of information. Atomic number, which tells us the proton, atomic mass or mass number, which gives us proton plus neutron. You have the charge here, and then your atomicity, which describes the number of atoms in a particular molecule. But we're not dealing with this other thing. We want to concentrate on one part. And what is the part we want to concentrate? Charge. So once you look at a substance and there is no value written here, it means that it is neutral. And according to our principle, the oxidation number of a neutral substance is equal. So the oxidation number for this guy will be 0. If I write H2SO4, because there is no charge in the whole molecule, the oxidation number of the whole molecule is equals 0. If I write SO42 minus, is this neutral? No. So the implication is that the oxidation number of this one is not equal to 0. However, once you write any other substance and you notice that there is no charge, it means that the oxidation number is equals 0. Okay, so let's go to rule 2. Rule 2 states that the oxidation number of a charged particle is equal to the charge it carries. And that simply means that once you are dealing with a particular particle and it is charged, the oxidation number of that particle will be equal to 0. I've indicated or explained what it means to say a particle is charged. Once there's a numerical value here, it means that it's charged. So the implication is that for this whole substance, because it has a numerical value here, it means that the oxidation number is equal to the charge. So which means for SO4 2 minus, the oxidation number will be equals -2. If I have NO3 minus, the oxidation number will be equals -1. If I have PO4 3 minus, the oxidation number will be equals -3. Why? Because the rule states that once you have a charged particle, the oxidation number is equivalent to the charge of that whole substance. Okay, moving ahead to the next one. The oxidation number of oxygen when combined is always -2, except when oxygen is combined in a peroxide where it becomes -1, or in oxyfluoride where it becomes +2. So let's take this down. Have this in mind, that anywhere you see oxygen combined, that is, when you see oxygen in a compound, for instance, in H2O, oxygen is combined here. The implication is that if you are looking for the oxidation number of oxygen inside water, the oxidation number of oxygen is going to be equals -2. Now, the only exception, or the only place where oxygen changes its oxidation number when it is combined, is in a peroxide. Like in hydrogen peroxide, the oxidation number of oxygen here is going to be -1. As we said, in sodium peroxide, the oxidation number of oxygen is going to be -1. However, in any other substance, you have CH3, COOH, this is ethanoic acid. The oxidation number of oxygen here is -2. You have H2SO4. The oxidation number of oxygen here is -2. So you have that anywhere you see oxygen combined with any other element, its oxidation number is going to be -2. The only exception is when oxygen is found in a peroxide, where it becomes -1, or in a situation where it is combined with fluorine to form the oxyfluoride, where it becomes +2. So that's that basically about oxygen. Okay, moving ahead, we go to the next one. What's the next one? The oxidation number of hydrogen when combined is always +1, except when it is combined with a metal where it becomes -1. So for hydrogen, anywhere you see hydrogen, like here, hydrogen is equals +1 here, hydrogen is equals +1 here. For its oxidation number, hydrogen here is +1, hydrogen here is +1. The only time oxidation number of hydrogen changes when it combines with other elements is when hydrogen combines with a metal. So when hydrogen combines with sodium, it becomes -1. When hydrogen combines with nitrogen, which is a non-metal, it is still +1. But when hydrogen combines with calcium, for instance, to form your calcium hydride, it becomes what? -1. So metals combining with hydrogen makes the oxidation number of hydrogen to become -1, because in this case, hydrogen will have to accept electrons instead of sharing or donating. So have that in mind. When hydrogen combines with any other element, it becomes +1. But once it combines with a metal, it becomes -1. These points should be taken note of because they would help us in solving the questions we're going to be solving. We now go to the next one. The oxidation number of your main group metals when combined is equivalent to the group or their group in the periodic table. So you have that every metal or every element is classified or placed in the periodic table according to its group. Group 1 metals would basically have the oxidation number of 1. So whenever a group 1 metal combines with a substance, so K2SO4, you will notice that because we know that this is a group 1 metal, the oxidation number of potassium would now be +1. If, for instance, I am dealing with calcium in calcium sulfate, the oxidation number of calcium in calcium sulfate, because calcium is group 2, it is going to be equals +2. I know that I have a compound AlOH, which is aluminium hydroxide. If I need to know the oxidation number of aluminium here, all I need to do is understand that the group of aluminium is group 3. Hence, when aluminium combines, it has the oxidation number of +3. I presume this is quite understood, so we move ahead. Then we go into the next one. The algebraic sum of oxidation numbers of constituent elements in a neutral substance is equals 0. So what does this mean? That if you have a neutral compound or a neutral substance, and you begin to add their oxidation numbers of the individual elements, it will eventually give us 0. It actually does make a lot of sense. If we take this all out and then consider this, H2SO4. If you add the oxidation number of hydrogen, mind you that there are 2 of them, so times 2, to the oxidation number of sulfur, to the oxidation number of oxygen here, mind you that there are 4 of them, so times 4. The rule states that it is equal 0 because there is no charge. So that's that. So if I have this, I can use this to actually resolve for the oxidation number of an unknown in this case. Take, for instance, we are asked to find the oxidation number of sulfur. We already know that hydrogen's oxidation number is always +1 when it combines. So this will be +1 times 2. Plus, we don't know what sulfur is, so let's put S. Then we already know that oxygen, anytime it is combined, has the oxidation number of -2. So -2 times 4 will be equal 0. So if we do this, making S the subject of formula, we are going to have, okay, before that, let's basically take it in sequence. 1 times 2 is going to give us 2 plus S. -2 times 4 is -8 equals 0. So making S the subject of formula, that's going to be 8 crossing over will be 8. -8 crossing over will become +8, then 2 crossing over will become -2, and S is going to be equals +6. So you have that. Now, whenever you are asked to find the oxidation number of individual elements, simply add them all up and equate them to 0 if the compound is neutral. Let's try something else. Imagine we had something like, let's say K2Cr2O7. This is your potassium heptaoxodichromate. Let's find the oxidation number of chromate here. Now, as I said, is this neutral? Yes. And once it is neutral, according to our rule, the rule simply states that the algebraic sum of the oxidation number of constituent elements in a neutral substance is equivalent to 0. So we are going to be making this equal 0. So that means we are going to have K times 2, adding it to Cr times 2, adding it to oxygen times 7. And because it is neutral, all of them equals 0. Now, mind you, potassium is a group 1 metal. And we said that once you have a main group metal and it combines, the group of the metal is equivalent to its oxidation number. So this is going to be +1 times 2, plus we don't know what chromium is, so that's going to be 2Cr. Then oxygen is always -2, anytime it's combined, except in peroxides and oxyfluoride. This is not a peroxide, this is not oxyfluoride, so this is minus 2 here. So minus 2 times 7, all of them equates to 0. So this is going to be plus 2 Cr, minus 2 times 7 is minus 14 equals 0. So if you cross over, it will become 2Cr plus 14 minus 2. And this is going to give us 2Cr equals 12. Dividing through by the coefficient of Cr, we are going to have that the oxidation number of Cr will be 6. Hence, the name of this compound is going to be potassium heptaoxodichromate 6. And that's the oxidation number. Okay, I presume this was well understood, so we go back to our rules. Now, going back to our rules, we'll find that the last rule says the algebraic sum of the oxidation number of constituent elements in a radical is equal to the charge it carries. So the question first is, what is a radical? Now, a radical is simply described as a group of elements which usually possess charges. So for instance, if I have SO4 is a group of elements and then it has a charge, this is a radical. And what is the rule saying? That when we add them algebraically, we are going to have that the sum of the algebraic sum of the individual elements in a radical is equal to that charge they are carrying, and this is minus 2. So if, for instance, I had something like MnO4 minus, this is a radical because I can see a group of elements and they have a charge. So which means if I add Mn to oxygen into 4 places, as we can see, it is going to give me minus 1. So let's find the oxidation number of Mn here. So this is going to be Mn. Oxygen is always minus 2, so this will be minus 2 times 4 equals minus 1. So this is now going to give me Mn minus 2 times 4 is minus 8 equals minus 1. And if we make this the subject of formula, Mn is now going to be equals 8 minus 1, and Mn is going to be equals plus 7. So if we are to name this, this is going to be tetraoxomanganate 7 because the oxidation number of manganese here is 7. If we are to solve for this, quite simple. If we continue from here, this will be S plus oxygen is always minus 2 times 4 equals minus 2. So we have that this is going to be S. Remember, this minus 2 is the total charge of the radical, so that's it. So this is going to be equals 8 minus 2, and S is going to be equals 6. So this is going to be tetraoxosulfate 6 ion. I presume this was easy to understand. So we are going to get into solving some important Jamb questions to help us buttress this point. So let's start with this. The oxidation number of chlorine in potassium chlorate is dash. I think the first thing you need to know is what is potassium chlorate. Potassium chlorate has the chemical formula of KClO3, and its IUPAC name, if you know it, you already have your answer, is potassium trioxochlorate 5. However, let's take for instance that you don't know that the answer to the oxidation number is 5. How are you going to resolve this? Very simple. Now, let's get to work. If we are to write down the chemical formula, we are going to have KClO3. And what are you noticing? This is a neutral substance, which means if we add potassium's oxidation number to chlorine's oxidation number to oxygen, we have 3 oxygen. Because it is neutral, is equal to 0. So let's find out of chlorine. Very simple. This is going to be K. K is a group 1 metal, so it's plus 1. Plus chlorine, we do not know. Oxygen is always minus 2 when you combine it. So this is going to be minus 2 multiplied by 3. And when you have that, this is going to be equal to 0. Now, plus 1 plus Cl minus 2 times 3 is minus 6 equals 0. Hence, what do we have making Cl the subject of Ma? Cl will now be equals 6 minus 1, and Cl is equals plus 5. That was quite simple, I guess. Also, do make sure you go through this as many times as possible to help you understand this concept. Now, moving ahead, let's try more questions. What is the oxidation number of carbon in HCOOH? This is methanoic acid. And as I said, it's quite easy to understand these things, basically, once you are able to understand the application of the rules. As you can see, it's going to give us our answer without any hitches. Now, let's get to solve. Taking this out, you would find out that we have methanoic acid, HCOOH, is a neutral substance, which means if we add everything, it's going to be giving us 0. So we have H plus C plus O plus O plus H would be equals 0. And that means that hydrogen will have the oxidation number of plus 1. Carbon will have, we don't know what carbon is, we are looking for that. Oxygen has the oxidation number of -2. The second oxygen is also -2. And then hydrogen is +1 equals 0. So let's add that up together. +1 plus carbon -2 -2 is going to give us -4 plus 1 equals 0. If we resolve that, C is going to be equals 4 minus 1 minus 1, and C is going to be equals 4 minus 2. Therefore, the oxidation number of carbon is going to be equals +2. Quite simple. So once you're able to understand the basic rules, once you're able to understand the basic principles, you will notice that solving for oxidation number will not be an issue for you. So if we are to go back to the rules, we will notice something. What are the rules we will notice? First of all, oxidation number of a neutral substance is equal to 0. Second of all, the oxidation number of a charged particle is equal to the charge it carries. Oxygen is always -2 when it is combined. Hydrogen is always +1 when it is combined. With those exceptions, as you can see, the oxidation number of group 1 metals is equals +1. That's the main group metals simply coincide with the group in the periodic table. Algebraic sum of the constituent oxidation numbers of elements in a neutral substance is equivalent to 0. And finally, you have that oxidation number of a radical is basically the sum of oxidation numbers of elements in a radical is basically equal to the charge it carries. With this, I presume you are able to solve questions with respect to oxidation number. Welcome guys to Efiwe, Excellence Without Stress. And I remain your favorite chemistry tutor, Godson. In today's section of the study, we are going to be considering reducing and oxidizing agents. Now, all you need to know is that a reducing agent is characterized by its properties, while the oxidizing agent is also characterized by its properties. So, once you are able to consider the properties of these things, automatically, you've gotten your answer. Starting with the first one. Also, you should also take note of the fact that a reducing agent should have opposite properties to that of oxidizing agent. But let's get into it. Reducing agents induce reduction to the other reactant. So they themselves are not reduced, but they cause reduction to the other reactant. Now, on the other hand, they are oxidized. So when they are causing reduction to the other reactant, what is happening to them is the opposite process, which is that they are oxidized. Now, if you say that they are oxidized, and oxidation is the loss of electrons, remember our acronym, OILE, RIGE, O-ion, radon, which means oxidation is lost. So once a reducing agent is oxidized, it loses electrons. And a loss of electron would actually lead to an increase in their oxidation number. So these are the properties. Anytime you're answering a question with respect to reducing agents, feel free to always come back to this, look through them, and answer your question. With time, you get conversant with these things. Going to oxidizing agents, they are going to have the exact opposite properties, which are they induce oxidation to the other reactant. They are reduced. After they cause oxidation to the other person, they themselves become reduced. They gain electrons, yes, because they are reduced, reduction, gain of electrons. And then finally, their oxidation number decreases. Now, let's consider some questions to help us understand this. If Y is an oxidizing agent that reacts with a reducing agent Z, which of the following is correct? Now, if Y is the oxidizing agent, what can we get from Y as the oxidizing agent? It is supposed to have or cause oxidation to Z. If Y is the oxidizing agent, it's supposed to cause oxidation to Z, which means it is also going to be reduced. Now, when you say that Y is going to be reduced, it implies that Y will gain electrons, or there will be a decrease in the oxidation number of Y. Let's now look at the option. So we have Y increases in oxidation number. Remember, they said Y is the oxidizing agent. So let's check. Is Y as an oxidizing agent supposed to increase in oxidation number? No. So which means option A is wrong. It's supposed to decrease. Y becomes reduced. Let's look at that. As the oxidizing agent, is Y reduced? Yes. So which means B is the correct answer. But let's confirm to see if it actually coincides. You will notice that they said that in option C, Z or Z loses protons. Please, redox reaction does not have to do with protons. So option C and D is definitely wrong. Moving ahead. The next question says, in the above reaction, the reducing agent is dash. Now, this is supposed to be a very simple question. We're going to go back to our board so that we can be able to solve this question without any hitches. Now, we would have to take down the reaction. AgNO3, pH3, water, Ag, and H. Okay, so taking this down, we are going to have AgNO3 reacting with phosphine. And when this reaction occurs, there's water present. And what is going to give? So let's go back to our question. So we'll see that to give silver, H3PO3, and then HNO3, basically. So it's going to give silver plus H3PO3 and then HNO3. Now, for us to be able to find the reducing agent in this question, as I said, we would always refer back to our properties. The reducing agent has these properties. The reducing agent induces reduction, but then that reducing agent is oxidized. It would lose electrons, or there will be an increase in its oxidation number. So let's check for the substance that has these particular properties. Let's look at our board. Now, balancing of it doesn't necessarily affect the oxidation number, so you can have it like this and then still solve. So we're going to find the individual oxidation numbers of all these elements here, and once you find that, it's going to be easier for you. Now, silver is usually univalent. Just take note of that. It's one of the elements or metals that you should take note is univalent. Silver is univalent. And because silver is univalent, we'll have +1. Now, let's find the oxidation number of nitrogen here. How do we do that? Ag plus N plus oxygen times 3. As we know, according to the rules, if you add the oxidation number of neutral substances, it equals 0. So this is going to be +1, as we know, plus nitrogen, plus oxygen, which is -2, times 3. And that's going to be 0, which means that we're going to have N will be equals 6 minus 1, and N is equals 5. So here we have 5. Oxidation number of oxygen is always -2. Then phosphorus here is phosphorus. Let's find out. So that's going to be P plus H times 3 equals 0. That's P plus +1 times 3, which is equals 0. So therefore, P is going to be equals -3. So here phosphine is going to be equals -3. Okay, take note of that. Then hydrogen is +1. Then here hydrogen is +1, oxygen is -2, as we always know. Then moving ahead here, there is no charge, so here is 0. Then here we have, let's find that of phosphorus here. So that's going to be H times 3 plus P plus oxygen times 3 equals 0 because it's neutral. So that's going to be +1 times 3 plus P plus -2 times 3 equals 0. So that's going to be 3 plus P minus 6 equals 0. And P is going to be equals 6 minus 3, and that is 3. So here we have that this is going to be +1, +3, and -2. So here it's still the same thing. We can solve it if we want, but it's still going to give us the same thing. This +1, +5, and -2. Okay, so let's note something. Silver here used to be +1, but when it crossed over to this side, it became 0, which means it's reduced. Reduction occurred. There was a decrease in oxidation number. So let's look at our features. If reduction occurs, which of these substances is responsible for reduction? You'll notice that the oxidizing agent is what is reduced. Oxidizing agent is reduced while reducing agent is oxidized. So because silver in AgNO3 was reduced, the implication is that it is the oxidizing agent. So you can put that down, that this is the oxidizing agent. Now let's consider this. Phosphorus here used to be -3, but then when it crossed over, it became +3. From -3 to +3 is an increase, and that is oxidation. So which of these two agents is involved in oxidation or is oxidized? You notice that that is the reducing agent. The reducing agent is oxidized. Hence, you would have that. So you will have that your phosphine is going to be the reducing agent. So just have that in mind. It's quite basic. So let's go back to our question to confirm that. Now, the other guys are just spectators. They don't affect the reaction in any way. So they said, in the above reaction, what is the reducing agent? As we said, the reducing agent is characterized by the following properties. Number 1, they induce reduction. Number 2, they are oxidized. Number 3, they lose electron. And number 4, their oxidation number increases. So if you look at this, amongst these substances, when we go back to our board, the substances that coincides with this property is going to be phosphine, because phosphine was oxidized because its oxidation number increased from -3 to +3. That is oxidation. Hence, it is a reducing agent. So always have that in mind, that you should check the properties and compare them, and you have your answer. Quite simple. Moving to the next one. In which of these reactions does hydrogen act as in which of these reactions does hydrogen peroxide act as a reducing agent? So we are looking at where it acts as a reducing agent. So what should we look out for a reducing agent? A reducing agent should be oxidized, which means the oxidation number should increase. So whenever you are looking out for hydrogen peroxide, you are looking out for where the oxidation number of hydrogen peroxide or any element in hydrogen peroxide increases. That is because it is a reducing agent. So we are looking out for an increase in oxidation number. Okay, so let's look at the options and get ourselves acquainted. Now, if you are considering the oxidation number in option A, here oxygen is -1 because in peroxide is -1 and hydrogen is +1. But going over to water, oxygen becomes -2. From -1 to -2, you will notice that it is a decrease. But as we said, the reducing agent should have an increase in oxidation number. So it means that option A is definitely wrong. We go to B. Oxygen here in peroxide. We are considering the peroxide. That's why we're not considering any other element. We're considering just the hydrogen peroxide. So you have that here. The hydrogen peroxide here has oxygen as -1 and hydrogen as +1. If we go over, you have water. Oxygen in any other thing besides peroxide is -2. So it decreased from -1 to -2. Decrease is for oxidizing agent. Increase is for reducing agent. You will soon get accustomed to that. Just keep using them often and you get acquainted. Now, same thing happens here. You have that oxygen here is -1, hydrogen is +1, but over here is +1 and -2. So decrease, meaning that here it is acting as an oxidizing agent. But when we come here, you will notice that this particular hydrogen peroxide was converted to oxygen. That is, one of the oxygens here becomes oxidized to oxygen. If you notice, there is no oxygen here, but let's continue. So which means +1, -1. But here it goes from -1 to 0. Because you are noticing an increase from -1 to 0, it means that the answer is D. Why? Because a reducing agent, hydrogen peroxide as a reducing agent, should have an increase in the oxidation number of hydrogen or oxygen from its initial state to another. And the only place where you have an increase in the oxidation state of oxygen is in option D. So it went from -1 here to 0. From -1 to 0 is an increase. Hence, hydrogen peroxide is acting as a reducing agent in this reaction. And that's that basically. We have come to the end of this particular concept. Welcome guys to Efiwe Excellence Without Stress, and I remain your favorite chemistry tutor, Godson. In this section of our study of redox, we are going to be considering the rules for balancing ionic redox equation. So let's continue. Now, whenever you're asked to balance an ionic redox equation, it's important that you take note of these rules. And following them chronologically would actually prevent some certain mishaps with respect to understanding how to solve these questions. Okay? So let's start with the first one. The first thing you need to do is to identify the oxidation and reduction processes in the reaction. So we're going to be taking a question and applying these rules as we go on in the question. So the question we're going to be taking is, we're going to be balancing this redox reaction. So we have MnO4- plus Cr2 3 plus. Okay, let's make that Cr2O3 reacting to give Mn2 plus Cr2O72 Okay, so that's that basically. So we're balancing this particular guy. Now, I'm going to be taking out some parts. Once I apply the rule, I'll take it out and then we continue from there so that we'll be able to have all our the board will be able to fit into most of these things. Okay, so moving ahead, the first thing we need to do is to identify the oxidation and reduction processes in the reaction, and it's quite simple to do that. How do we do that? You have to find the oxidation numbers and check for increase and decrease. Now, manganese here has the oxidation number of 7. How do we know? So we have Mn plus O times 4 is equals minus 1. According to the rule of finding oxidation number, Mn, oxygen is always minus 2. So it's minus 2 times 4 equals minus 1. Then we have Mn minus 8 equals minus 1. Therefore, Mn is going to be equals 8 minus 1. Therefore, Mn is equals plus 7. So apply the same principle to the rest of them and you have your answer. So I'm going to be taking it out and putting down the different values for their oxidation number. There are different oxidation numbers in this particular question. So usually, oxygen is most times a spectator and hydrogen, unless you see a change from oxygen combined to it uncombined or hydrogen combined to it uncombined. But in most cases, oxygen does not change in oxidation state once it's combined. So don't concentrate on oxygen. The most important things are the other elements there. So here, manganese, you have that it's plus 7 here. Chromium here is plus 3. Manganese here is plus 2. Chromium here is plus 6. So we're going to be checking where oxidation occurred. Now, if you noticed, you will notice something here. Now, manganese went from plus 7 here to plus 2. And that is a decrease in oxidation number. Decrease in oxidation number is reduction. However, the agent involved in reduction is oxidizing agent. It gets quite simple, and I hope you understood this. Now, we've studied this in a different video. But here, chromium went from plus 3 to 6. And when it goes from plus 3 to 6, it's increasing, and that is oxidation. So we're going to do the first principle, identify them. Then we go to the next rule. The next rule now says we should split the reactions into reduction and oxidation half equation. So let's split that particular reaction. How do we split them? By just separating them into two. So we have that for the reduction, it would be MnO4 minus reacting to give Mn2 plus. That is reduction reaction or half equation. While the oxidation will be Cr2O3 reacting to give Cr2O7 2 minus. So that's that basically. And this is the oxidation reaction. Okay, now, having said this, we go back to our rule. The next rule is balance the elements on both sides of both equations except hydrogen and oxygen. So we're going to be balancing every other element, but we're not going to balance oxygen. We're not going to balance hydrogen. So it's simply because balancing of hydrogen and oxygen has a different method. So you have that this is Mn, there are one element of Mn here, one here, so it's balanced. Two elements of chromium or two atoms of chromium and two atoms of chromium here, so it's balanced. But if you had this situation where, let's say you had C2O3, 2 minus, and then you had something like CO2. If you are going to be balancing this, this is 2 here, this is 1, so you put 2 here and it balances out. So that's that basically. This is C2O4 instead. So that's that basically. For a situation where the elements are not balanced, you should balance them before you talk about oxygen and hydrogen. Now, we go to the next step. The very next step has to do with balancing oxygen. It says to balance oxygen, add water molecules to the oxygen deficient side. Note, the number of water molecules added is equivalent to the number of oxygen atoms required to balance the equation. So let's consider that. So if you notice, for this first reaction, which is the reduction reaction, you will notice that there are 4 oxygen atoms on the reactant side and there is none on the product side. The rule simply says to that side where you need to add or augment, instead of adding oxygen, you add water molecules. So we're going to have that this is going to be MnO4 minus reacting to give Mn2 plus. Then we add our oxygen. Instead of adding oxygen, we are supposed to add water molecules. So that is going to be H2O. Now, if you go back to the note says that the number of water molecules added is equivalent to the number of oxygen required to balance the equation. So if you noticed, we have 4 here and we have none here, which means we need 4 oxygen atoms to make it equal. So how many water molecules are we going to be adding? 4. That's that. Okay, so let's come to this. In the case of the oxidation reaction, so the oxidation reaction, we have Cr2O3, and then it is reacting to give Cr2O7 2 minus. So notice that here we have more oxygen than here. And because we have 7 here and 3 here, we will need 4 more to make this side equivalent to this side. Now remember, instead of adding oxygen, we are advised and asked to add water molecules. So 4 water molecules. And that's that. You've applied that rule. This is the reduction reaction, while this is the oxidation reaction. Okay, so moving ahead, we continue the rule. Just keep following it step by step. Now, the next thing is to balance hydrogen, add hydrogen ions or protons. So don't just add hydrogen atoms, add hydrogen ions. That's how hydrogen is being balanced. So let's get to that. It means that for our reduction process, all we need to do, so I'm taking this step from here. We'll continue from here. So how it flows is from here we went to here. Okay, so from here we went to here, and then from here we went to here, and now from here we are going to here. Okay, so just keep flowing with us. Now, with that said, for the reduction reaction, we are going to balance out hydrogen. MnO4 minus reacting to give Mn2 plus 4H2O. So if you notice now, we don't have any hydrogen here, but we have 8 hydrogen atoms here. So the implication is if we are going to balance it according to the rule, we are supposed to add hydrogen ions. And how many are we adding? 8 hydrogen ions. It's quite simple. Then for the oxidation, remember this is where we are now, so we continue from the step. We have Cr2O3 plus 4H2O. And then this is going to be reacting to give Cr2O72 minus. If you look at this, you will notice that there are 8 hydrogen atoms here, which means we need to add 8 on this other side. How do we add it? By adding 8 hydrogen ions, not atoms. This is an atom of hydrogen, this is an ion of hydrogen, this is a molecule of hydrogen. Please do not misplace those things. So we are asked to add ions because it is going to affect the charge. So we are done with this step, and then we'll be moving to the next step. Now, what is the next step? Let's look at that on the screen. Okay, I'm trying to bring it up so everybody can see it, basically. Okay, so now you can see it. Now, the next step is that we should balance the charges on both equations by adding electrons. Now, points to note. Electrons are added to the right side of the oxidation equation, while they are added to the left side of the reduction equation. So we're going to be adding electrons. To bring about a balance of the charges, we need to add electrons. Now, I am going to have to take out this whole thing on the screen, but let's take note of the fact that this is where we stopped. So just have that in mind, that this is where we are going to pick it up from. Just to give us more room to solve, I'm going to take it all out. Now, where we stopped, as I said, the reduction reaction is basically equivalent to MnO4 minus plus 8H plus reacting to give Mn2 plus that's going to be 4H2O. Okay, now we now have that the oxidation reaction is Cr2O3 plus 4H2O reacting to give Cr2O72 minus plus 8H plus. Yeah, so that's that basically. Now the rule, applying the rule says, let's read it together. Balance the charges in both equations by adding electrons. Note, electrons are added to the right side of the oxidation. So when we are adding electrons, we add to the right side, while they are added to the left side of the reduction. So let's do that. This is the reduction reaction. We are asked to add to the left side. So if we are writing this equation is going to be written like this. So for the reduction, you would have reduction reaction. Reduction reaction will now be MnO4 minus plus 8H plus. Now you are adding electrons to the left side of the reduction. So that's going to be here plus Xe minus reacting to give Mn2 plus 4H2O. Now, before we come down to oxidation, I would like us to find this X, and it's very simple to find. How many electrons exactly are you going to add here? There's an easy method and there's a long method. I will teach both methods. Let me start by teaching the long method. Now, in the long method, all you need to do is equate all these charges, hanging numbers, equate them together and find the value of X. So let's get to it. Now, what is the charge you can see in this particular substance? -1. Now you have -1. Now, but note, how many -1? The number here multiplies this charge directly. So this is -1 times 1. So that's that. So we have plus. Here, the charge we have here is plus 1. How many plus 1 do we have? We have 8 of them. So plus 1 times 8. Then we come down here. The electron has a negative charge of minus 1. How many of them do we have? We have x of them. So we are looking for x equals. We have plus 2 here. How many plus 2 do we have? They're just 1 Mn. So plus times 1. Then here we have 0 as the charge. How many zeros do we have? 4 zeros. So moving ahead, this is going to be minus 1 times 1 minus 1. Plus 1 times 8 plus 8. Minus 1 times x minus x. Plus 2 times 1 is equals plus 2, and then 0 times 4 is 0, so we don't need to put that there. So this is going to be minus x equals, going over, this would now be minus 8 plus 1 plus 2. And if you do this, minus x is going to be equals minus 5. Now, cancelling out, x is equals 5. Now, remember, you can go back to review this step again to understand it, basically. So we have that instead of writing x, our reduction reaction is going to be giving us Mn O4 minus plus 8H plus, in place of x, we are going to have 5 electrons reacting to give Mn2 plus 4H2O. So that's basically how to find the electrons that, in this case, reduction, meaning that it was gained. That's why it's added to the left side. So that's that basically about this. Now, for the shortcut method. For the shortcut method, all you need to do is look at the oxidation number of the substance, the element, not the substance, but the element that is being oxidized. So in the case of this particular guy, we have that the element oxidized here is manganese. So considering manganese, we have that the oxidation number of manganese itself is plus 7. How many manganese elements do we have here? We have 1, so times 1. So is there any other manganese here? No, so we're not adding. Now, you come to this other side and find the manganese here. The manganese on this side is plus 2. So, now, for your reduction, you use the left-hand side to minus the right-hand side. So, to get x is equals left oxidation number of element minus right oxidation number of element, while in your oxidation process is going to be right oxidation number minus left. Okay, so let's continue. Or just simply know that the big oxidation number minuses the small oxidation number. So that's going to be 7 times 1, then minus. What is the oxidation number of manganese here? Plus 2. How many do we have? So we have plus 2 times 1. So it means that the value of x in this case is going to be 7 minus 2, and that is 5. So this is the shortcut method, but it can be confusing in some cases, especially when you have multiple of that element. You can get confused. So preferably follow this process and you have your answer. Now, let's solve for that of the oxidation number. So if you did not get it while we are doing this, please take note and eventually get it now. So remember, for an oxidation equation, we were asked to add it to the right side. If you'd notice, we were asked to add it to the right side of the oxidation number. So let's continue. So for the oxidation reaction, I meant to say, we're adding the electrons to the right side. So this is going to be Cr2O3 plus 4H2O reacting to give Cr2O7 2 minus plus 8H plus. Then because we're adding the electrons to the right side, that's this side of the equation, that's going to be plus Xe minus. So as the rule says, you are adding the electrons to the right side. Remember, this is left, this is right. So that's why we are adding the electrons here. Why? Because the electrons in oxidation is lost from this side to the other side. So just know it's lost, it's removed. So basically, that's why we have that in this case. So having said that, we'll have that, let's now find x, the long method. If you look at here, there is no charge, so it's 0. Please, the whole compound has this charge here, not the elements. The long method, you are looking at the charge of the whole compound, not the oxidation number. So in this whole charge, we'd have that the charge here is 0. So we'll have 0 times how many? 1. Plus, here is also 0 times how many? 4. Equals, here we have minus 2. And how many is it? 1. But here we have plus 1 as the charge. But how many plus 1s do we have? 8. Here we have minus 1 as the charge. How many minus 1s do we have? X. With this said, 0 times 1 is 0. 0 times 4 is 0. This is minus 2 times 1 minus 2 plus, this is plus 8, and then this is minus x. So if you take this all over, if minus x crosses, this will now be x is equals 8 minus 2, and that is going to give us 6. Okay, so that is for the long method. Now, short method. We have that here for x in oxidation. X is going to be equals right oxidation number of the element involved minus left oxidation number. If you are confused about left and right, just know that the higher number is going to minus the lower number. So let's find it. So the oxidation number of the oxidized substance, chromium is the oxidized substance, not hydrogen, not oxygen. So we are considering only chromium. So here, oxidation of chromium here is +3. So X is going to be equals, okay, for right, let's find right first. So the right here, oxidation number is +6. But how many +6's do we have? We have 2 of them, so put them together. Minus, the oxidation number on the left side is +3. How many +3's do we have? We have 2. Look at the 2. Now, please note, when we are looking at charge, it's the whole substance, but here we are considering only the element oxidized. We considered only the element reduced to find this. So this is going to be X is equals 12 minus 6. Therefore, X is equal to 6. So whichever one you find easier for you, you can use them. Now, for the reaction, we are going to have that the final equation for the oxidation is going to be oxidation reaction will now be Cr2O3 plus 4H2O. And if we have that, it is going to be reacting to give us Cr2O7 2 minus plus 8H plus. Plus, instead of X, we have found X to become 6E minus. Okay, so take note of these things. Remember, you can go back and rewatch this video over and over to understand these stepwise processes. Now, I'm going to take these reactions and continue from here. I'm going to take everything out and then continue from where we are. So, writing the new equation we have, our oxidation reaction is Cr2O3 plus 4H2O. And that is reacting to give Cr2O7 2 minus plus 8H plus. And then we have our electron to be 6E minus. Then for the reduction reaction, what we got after balancing out the charges is MnO4 minus plus 8H plus plus 5E minus would be reacting to give Mn2 plus 4H2O. Okay, so let's go and continue the rules. Now, the next rule is that we should ensure that the number of electrons lost by oxidation equals the number of electrons gained by reduction. To do this, use the coefficient of electrons in the reduction reaction to multiply the oxidation half equation and vice versa. So it's more like when you are performing simultaneous equation and you are solving using elimination method. So we want to eliminate the electrons at the end of this. How do we eliminate them? We'll use the coefficient of electrons in oxidation to multiply the whole of reduction. So let's do that. So we're going to be using 6 to multiply the whole reduction reaction. But then when we want to now multiply the oxidation reaction, we will now take the coefficient of electrons in reduction to multiply that of oxidation. So let's do that together. Now doing this, we will now have that our new reaction for oxidation will now be multiplying all through. That will be 5 times Cr2O3. That will be 5 Cr2O3 plus 5 times 4H2O would now be 20H2O. And then reacting to give 5 times Cr2O7 2 minus, 5 Cr2O7 2 minus, and 5 times 8 plus would be, that's supposed to be 40 H plus, and then 5 times 6 is going to be 30E minus. Sorry about that. 30E minus. Okay, so then solving 6 multiplying through, we'll now have that for the reduction reaction. 6 multiplied by Mn will become 6MnO4 minus, plus 6 times 8 is going to become 48 H plus. And then plus 6 times 5 is going to be 30E minus. Reacting to give 6 times Mn, that's going to be 6Mn2 plus. And then 6 times 4 is going to be 24H2O. Now, we would go to the final process. The final process says combine both equations and remove redundants. Redundants are reoccurring species, things that occur that have occurred before on both sides. So let's look at them. So combining this reaction, we're going to put all the reactants together and all the products together. That's what it means. So putting all of them together, we are going to have a combined equation of 5Cr2O3. You can start from anywhere. You can pick one here, but just make sure the reactants are all combined and the products are all combined, plus 20H2O. Then we are done with this side. So let's continue with the reactants on the reduction. Plus 6MnO4 minus, plus 48H plus 30E minus. We're done with the reactants. Let's now combine the product. 5Cr2O7 2 minus plus 40H plus 30E minus plus 6Mn2 plus and then plus 24H2O. Now, having combined this, the next thing we are supposed to do according to the rule is to remove redundants. Redundants are reoccurring species. So let's remove every reoccurring species that is there. Now, what are the reoccurring species? The reoccurring species, as you can see, electrons. Please do not look at the numbers but the substances. So electrons, 30 occurred here, we will remove it. 30 occurred here, we will remove it. So you have water on this side and water on this side. Remember that you are supposed to remove everything. The smaller one, remove all the smaller one, then minus the value on the other side. So we're removing 20 from this side, 20 water molecules, so that it disappears from here. Then come to this side and minus that same number. So minusing 20 from 24, the remainder would just be 4. So instead of 24, we're going to have 4. Okay, then what else is redundant here? Hydrogen ion is redundant, so you find out there are 48 here and 40 here. So let's remove every hydrogen ion on this side, 40, because this is the smaller side. So remove 40 here and then minus the same 40 from here. When you do that, we'll have 8 remaining, which means here will be 8. Hence our final reaction is going to be 5Cr2O3 plus 6MnO4 minus plus 8H plus. Then there are no more electrons, so we go on. 5Cr2O72 minus plus 6Mn2 plus 4H2O. So notice that this is balanced. Let's confirm. So we have 10. How many chromiums do we have on this side? Chromium is 5 times 2, 10. How many manganese do we have on this side? Manganese is 6. How many oxygen do we have? This is 5 times 3, 15. 15 plus, this is 6 times 4, 24. 24 plus 15, we are going to have 9 for this and 39. So oxygen is 39. And then hydrogen is 8. So let's check for this side. Now chromium here is 10. It's 10, 5 times 2, that's the only chromium. Manganese is also 6. Then you have that oxygen. Let's find oxygen. 5 times 7 is 35. 35 plus 4 times 1 is going to give us 39. And then finally, hydrogen, as you can see, is 4 times 2, which is 8. So notice that this is now balanced completely. So these are the steps that you should follow. Once you follow these steps, you can be able to balance any ionic redox equation. Now, for Jamb questions, you might not be asked to balance equations. I just show you all these steps so you will note the individual processes involved. If you are given a Jamb pass question, what you are likely to do, let's consider question. The first question we are considering says, what is the change in the oxidation number of copper in the reaction? So we are going to look at the oxidation number of copper here and find how it changes or what it is on the other side. So let's get to solve. It's quite simple. Now, let's take this whole thing out first so that we'll be able to solve. Taking everything here out. Now, so we had that the reaction, as we can see, let's put it up, is Cu2S plus O2 reacting to give Cu plus SO2. So let's get to that. Cu2S plus O2 reacting to give Cu plus SO2. Balancing is not so necessary when you are looking for oxidation number, but let's just balance. You get? So that's going to be 2, and that's that basically. So let's get to work. Now, to find the oxidation number change, we need to check for the oxidation number of copper here. So copper here multiplied by 2 plus sulfur would give us 0. When sulfur is combined with a metal, usually it has the oxidation number of -2. So just take note of that. So this is going to be 2Cu minus 2 equals 0, and that's going to be 2Cu equals 2. Therefore, if we divide by the coefficient, we would have that Cu on this side is +1. So note, this is +1. Then copper on this side is going to be equal 0 because there is no charge. So notice that the oxidation number changes from +1 to 0, and that is a reduction, which means that this particular substance is going to be an oxidizing agent. Remember, if it is reduced, it is an oxidizing agent, but if it is oxidized, it is a reducing agent. Okay, so let's look at our options to see which of them is correct. And that is going to be option A. Very basic. Remember, we are asked to find the oxidation number, change the oxidation number of copper, not any other substance. Okay. How many electrons are removed from Cr2 minus when it is oxidized to CrO4 2 minus? Let's get to solve. So you have that this is going to be Cr2 minus being oxidized to CrO4 2 minus. So it's basic. We are going to use the shortcut method. The long method of solving this, or the proper method, I have explained in the earlier parts of this video, so look it up. Now, to use or solve this thing, first of all, ensure that the element that is oxidized is the same. So you have 1 and you have 1. Ensure that the number of elements oxidized is the same. If it's not the same, you need to balance it. So if there was 2 here, we would add 2 here. But as we see in the question, it is balanced. Now let's continue. Now, find the oxidation number here is -2. The oxidation number here is going to be Cr plus O times 4 equals -2. Now, having said that, the implication is that we would apply normal algebra. Cr plus oxygen is always -2 times 4, and that's going to be -2. So Cr is going to be equals -8 equals -2. Therefore, Cr is going to be equals 8 minus 2, and Cr is equals 6. So here we have that the oxidation number of chromium is +6. Remember what we said? If you are looking for the electrons, how do you do it? You simply use the bigger oxidation number to minus the smaller one. In the case of oxidation number, or oxidation process, I meant to say, the right minuses the left. So that's going to be +6 minus -2. And electron number would be equals 8. So if you look at this question, you will notice that our answer is D, and that is that. Okay.